session. We start with a 25-minute talk as usual. So our first speaker is Aaron Poole, who will talk about supersymmetric localization of n equals 2,2 theories on spindle. Please.
Okay, thank you. Okay, you can all hear me well, I guess. Yeah, so thanks very much for the introduction and for the opportunity to give a talk at this workshop. So yeah, today I'm going to be talking about supersymmetric localization of 2,2 theories on a spindle. And this is some work I've been doing as a postdoc at Kyunghee University in South Korea, in collaboration with other people all based in Korea, Im-Tak John, Hoo-Jung Kim, Naku Kim, and Ogniva Ray. This is still work in progress, but we have some results that I wanted to share with you guys, and yeah, we're getting there to finish this project. So what's the sort of the genesis of the idea behind this? Well, this is to do with recent, sort of in the last 4 years or so, supergravity solutions have been found in various supergravity theories, and they all sort of take the form of ADS, of, well, some dimensional ADS, with the product of O, where O is some orbifold space. So kicking off with these papers by Ferrero et al. In 2020. And in almost all of these solutions, a particular two-orbifold O that appears is this thing that I'm going to call, bold sigma in this talk, a weighted complex projective space, better known as a spindle. We've heard about these in a few talks already. And sort of part of the magic of these solutions is that despite the fact they contain orbifolds, they actually smoothly uplift, in many cases, into d equal 10 or 11 dimensions, where these orbifold singularities are then sort of smoothed out in this uplift. This sort of leads to the idea that, okay, these solutions look singular in low dimensions, but actually they are good candidates from higher dimensions, string theory, M theory, and so should contribute to the full quantum gravity path integral when one considers these geometries. So this sort of leads to the question of, okay, we can still say something interesting about these looking from lower dimensional perspectives. And of course, one would want to study these solutions via ADS-CFT duality. And so the idea is that the dual CFT here is going to live on some background involving this orbifold, this spindle orbifold. So exactly how the background looks is not depends on the theory. And a particular sort of striking example of how this spindle could appear in the background of the CFT is given by the conformal boundary of the Plebanski-Demiansky solution that we heard Yanis talk a lot about the other day, where the conformal boundary is this spindle, at least in the Euclidean case, with a product of a circle. So this is sort of an ADS-CFT motivation, but we can also say, what about just looking at supersymmetric QFT on such orbifold backgrounds? So what can we do? And of course, when we do this, we want to compute observables, and there's a very powerful technique known as supersymmetric localization, sort of initially applied on the force sphere by Peston. And we want to try and apply these kind of techniques to orbifold backgrounds. So there's already been some work done on this in the last 2 years for various theories in different dimensions involving different amounts of supersymmetry. So for 3D n equals 2 theories, there's two particularly striking examples. One, of course, is related very intimately to this this accelerating black hole conformal boundary, and the other one is on this this space lambda, which is a branched, squashed lens space. I'm not going to hear much about this in my talk, but I think there might be some mention of it in a later one. And also in 4-dimensional theories, such calculations have been performed on the product of a spindle and a torus, and this lens with a circle as well. So this is what's been done, but what I'm going to talk about today is sort of filling in one of the gaps of the theories that you might want to study, and that's just a 2-dimensional 2,2 theory living on just spindle. So there's no extra space here. Okay, so that's just the setup. Again, we've heard a bit about these, but since I'm sort of kicking off this session, I'll give a kind of an overview of what we mean by this spindle. So it's this weighted complex projective space, and there's two integers here, n1 and n2, which appear in the description of this orbifold space. And well, I'm going to take these two integers, well, to be sort of arranged in this order. This is not particularly important. Something that is important, particularly when one thinks about the uplift, is that you want to make these co-prime so that 1 is their greatest common divisor. Now, this again is not going to be relevant particularly in what I'm going to say, but this is sort of going to be here in the background. So what do these actually look like? Well, they're essentially spheres with some conical singularities present at each pole. So each pole is locally, not locally, well, the complex plane, but rather the complex plane modulo some integers. Again, modulo these two integers here. And so I've just highlighted here two different cases of spindles that one could have. So you can choose it. You can choose these integers such that one of the poles gets smoothed. But as I'll show you later, you can never really do it so that both get smoothed. So here's one with just one singularity, and here's one with two. And one of the very interesting features when we're thinking about supersymmetry on these guys, regardless of what supergravity we're thinking about, is that they have this condition on preserving the supersymmetry. So we want to put our U1R field with the spindle, and it's a condition that the flux of this through the spindle always has to obey the following formula. So this is required for supersymmetry. And there's sort of a difference here. Again, there was mentioned that you can either have sort of a standard case where this gives you the Euler number of the spindle, which would be where this parameter sigma is 1. So this is the sort of better known twist case. But then there's also this other case which is sort of seemingly very novel to these orbifolds, and that is to take sigma as -1, which will be referred to as the anti-twist case. So we'll see as we go through how this plays a role. Okay, so that's just the general overview of spindles. And I'm always going to also think about, sort of to guide the calculation I'm going to tell you about, I'm going to think about a particular supergravity solution involving a spindle. And I'm kind of going to take, perhaps the simplest one, but the first one that was found, which is just in d = 5 minimal gauge supergravity. So I'm not going to give you the details of the theory, it's sort of well known, but here's the solution. So the metric, of course, has this ADS3 factor with some warping. And then there's these two extra directions parameterized by these coordinates y and z. And this is the metric on the spindle. So y here is essentially like roughly related to the theta coordinate of spherical polars, and then z is an axial angular coordinate. So also notice that there's no z appearing in any of this, so z is the killing direction of the spindle. It has U1 symmetry. So there's this cubic polynomial that appears in the formula, and we want to set this metric up such that we have a positive definite metric. So you can do this sort of standard analysis of a cubic and see that you find 3 roots, and you want to pick some range of the coordinates where this, this whole metric is positive definite. So this just ends up in picking a restriction between the two smallest roots of this polynomial. And these 2 roots essentially are the poles of this spindle. And so you might sort of think, well, okay, and there's nothing really clear about why this guy is singular at this point. So you might just want to try and choose the period of this axial coordinate z to try and get rid of any potential conical singularities. And you quickly find out that when you try and play this game, that you really can't do it. So you can sort of set your, this parameter a that appears in the metric and your choice of the period such that you get rid of one singularity, so like this picture on the left, but you can never get rid of both. So this is, why you're always left with something. But you can sort of set up a choice of these guys. I haven't given the explicit form, but they're given in terms of these 2 integers, such that you have exactly the conical deficits that is present in this, the definition of this orbifold appearing at each pole. Okay, so that's just a very, very brief discussion of the metric I'm going to use for this calculation. But of course, we also have the R-symmetry gauge field. And I'm going to work with the same one that appeared in the original paper. And again, I mentioned there's this condition on preserving supersymmetry. And so if you look at the integral of the flux of this U1R symmetry gauge field through the spindle, you find that this is actually an anti-twist case. So the first solution found was was not twist, but anti-twist. That's the, less familiar way of preserving supersymmetry. And as a sort of a, well, this is kind of a technical point, but we notice that this choice of the gauge field is not regular at the poles of the spindle. So because these are the degenerate points, it would need to vanish for that to be the regular gauge. But this is singular. And so this is a technical point, but this will be important in the localization calculations. Some methods were allowed to work in this gauge, others not. Okay. Right, so that's the supergravity solution that we sort of want to have in mind for this talk. But of course, generally, we're not just thinking about supergravity, and we want to just look at 2,2 field theories living on this background. And so really we should sort of do this by not like necessarily thinking about a particular supergravity, but use this procedure to define the SUSY theory on a curved manifold that was originally described by Festuccio and Seiberg. So basically one just minimally couples the flat space SUSY theory to gravity, and then you take this rigid limit of sending the Newton constant to 0, which makes the supergravity non-dynamical, and just leaves you essentially with your SUSY theory on a curved manifold. Now, this can be done for, again, various theories involving various amounts of supersymmetry, but it's been very nicely described in detail in this paper by Closet and Cremonesi for 2,2 theories. And the key point of this paper that I just want to highlight for this are these two off-shell killing spinner equations. So we don't have to have, even solving the equations of motion for supergravity at this point, but you can still write down these equations. And the key point about these, so epsilon bar are just 2D Dirac spinners, tilde, and because we're in Euclidean, we're not going to impose any condition about conjugation. These are just independent spinners. And the key point about these equations is that we have two functions that sort of describe the way these differential equations are going to look. And they're not entirely free. They're constrained essentially by the integrability condition for these equations to be sort of constrained to be some function of the Ricci scalar of the spindle and the U1R field strength. But essentially there's two functions you can pick. And sort of now we're going to go back to this d equals 5 minimal gauge supergravity that I just mentioned. And what you can do is look at the full 5D killing spinner equations from that, reduce down on the ADS3 directions, and you can essentially read off what G and H are for this solution. And so the first thing that sort of struck us is that G is purely real, H purely imaginary, and this sort of choice manages to avoid all of the cases that people have studied thus far, which is not really surprising because it's a sort of different space. Just an example of some other things that people have looked at. I mean, spheres and squashed spheres often take 0G. Euclidean ADS2, so hyperbolic space, was analyzed with a 0H. And then there are other cases like the A-twist and omega deformation, where some combination of H plus minus IG vanishes. So this is clear. This is not supposed to be exhaustive of all the things you can have, but this spindle case is clearly falling out of any of the classes that people have looked at below. Okay, so we're going to kind of work. So I should say we're going to work through this calculation sort of with these choices from the minimal d equals 5. Yeah. Okay. This is just schematic to say that there's some function of the reaches. Essentially, I think it's essentially minus 2 times this plus some constant multiplying the field strength. So, it's just schematic. Couldn't fit in the full formula. Yes, please.
I guess what hasn't studied is localized theories on disk.
Right, that hasn't been done. Yeah. So that's so disk. By disk, you mean like a half spindle, or you mean just a?
So you start with a disk.
Yeah.
Maybe those answers are there, and you can only group them together with the condition you put. You have some flux condensation condition.
Right.
The answers are related.
Yeah. So
I don't know if this with oracles has been done.
Yeah, that's the point. Yeah. So I don't think that has been done. So that would be an interesting thing to look at. But yeah. Okay. Yeah, okay, so I'll go on to discuss what I mean by doing supersymmetric localization. This has been mentioned a lot, and I just have one slide to sort of, briefly illustrate what I'm going to be doing with this. So we want to compute observables for our theory on the spindle. And, the observable we're going to compute really is just the partition function for this, using supersymmetric localization, in the style of Peston's original paper. So we have our 2,2 theory, which is, of course, a supersymmetric theory. And so the action is invariant under being hit by some equivariant supercharge, QEQ. And from our d equals 5, we're going to construct this essentially by adding up the two supercharges related to the two killing spinors, epsilon and epsilon tilde. So we have our supersymmetric theory, and we want to look at its path integral. And the basic idea is that you just deform this path integral by some Q-exact object, and this object has to satisfy sort of Q squared acting on it, annihilates it. So Q squared is some combination of bosonic symmetries. Basically, it's you can sort of think of this as the Lie derivative in the direction of this axial killing vector plus some U1R and gauge stuff. So when you deform the path integral using this, you get the following formula. And we've deformed it using this parameter t, which is a so-called equivariant parameter. And sort of the magic about this whole thing is that it's actually independent of this parameter t. So you can show this essentially by using all of these equalities I've shown, using the equivariant operator here as sort of an exterior derivative over the space. And so because it's independent of t, we can essentially take t to whatever we want. And if we pick our choice of perturbation here, this localizing action, to have positive bosonic part, then it makes sense to take t to infinity. And the integral will just localize to the fields which basically, of which this action vanishes and of which its first variation vanishes, which is the so-called BPS locus of the theory. So basically, this whole path integral is just reduced down to a simpler integral over this BPS locus, these classical saddles. And you can actually show that, of course, when you compute the path integral in this way, it's actually one loop exact. So essentially what you get is just the classical action evaluated on these saddles. And then there's some superdeterminant here, which is the ratio of the second order fluctuations between the bosons and the fermions. So all we want to do, really, for our theory is to compute this S det term that appears in the partition function. So we want to do this for the spindle. And the point is we want to do this one loop, this Z1 loop. And I'm going to sort of not do it for the most general theory just to illustrate this, but just to do it for a chiral multiplet on the spindle, which actually takes care of most of the work for you. So this is two complex scalars, two Dirac fermions, and then some auxiliary fields, F tilde. I'm realizing F is a bad notation now, but these are not going to appear other than in this formula. And the nice thing about this chiral multiplet is that it's very easy to just look at the BPS locus being basically all fields vanishing. So, the background is very, very simple. So really, so what do we do now? We pick our localization scheme. So this is a very standard choice of localizing action that one may want to pick. And sort of the way we kind of massage this calculation around is to rearrange the fields that appear in the chiral multiplet on the spindle into so-called cohomological variables. So these are just capital phi and psi. Now the capital phi is just packaging the bosons together, and capital psi is doing almost the same thing for the fermions, except we're twisting them by multiplication by the killing spinors in this certain arrangement. And so the aim of the game now is essentially to take your cohomological variables and rewrite this localizing action using them. And when you do this, you find that this sort of quadratic term in the fluctuations gives you a very nice ratio of determinants of this Q squared operator, one acting on the fermions in the cohomological variables and one on the bosons. So it becomes this nice compact formula, which is still not particularly easy to compute. So now I'm going to give you two ways to do that, and they will agree nicely at the end. Okay. Right, so the first method is sort of an older method, known as the method of unpaired eigenvalues. And the idea behind this is to utilize the supersymmetry to cancel a lot of the potential contributions that would appear in this one loop determinant. So the sort of aim of the game here is to find some operator which both pairs, sort of maps the bosons to the fermions and vice versa, and also commutes with this equivariant squared operator. And so the reason that these properties are nice is that every time, for example, if you have eigenvalues of this operator over the bosons, well, it's very important that these are non-zero so that you can compute these determinants. You can sort of use the following chain of equalities, so you can sort of look at the same thing acting on the fermions in the cohomological complex, and sort of push around, using the formulae up here, so essentially writing psi as O phi, then commuting, and then noting that, this is just an eigenvalue. You find there's a fermion of identical eigenvalue. So basically, every time you have, a sort of super partner here, these are just going to cancel in this one loop determinant. So they're not going to give you anything. So this tells you that sort of this has to break down at some point for things to contribute to this one loop determinant. And it turns out, of course, that if we have things in the kernel of this operator, then these will contribute non-trivially to this one loop formula. And similarly, the fermions will contribute in the Hermitian conjugate of the operator O. So we can actually build O very nicely. 5 minutes, yeah, great. Using our killing spinners. So these are just particular bilinears of the killing spinners. And then, one can sort of really explicitly turn the handle, examine the kernels of these operators and their conjugates, and you can work out everything that contributes to this one loop determinant. Now, I've sort of skipped all the steps and just put the result, which still looks a little bit messy, but is actually, well, I think quite neat, just the ratio of two gamma functions. So you see there's a bit of a mathematical structure in here, so there's a lot of appearance of floor functions. So this is the greatest integer less than or equal to the object inside the brackets. And there's also these double square brackets, which is sort of the remainder of integer division by the object in the bracket by the index in the bottom right-hand corner. And something you should notice that this is all done for the anti-twisted case. So the result that was shown for the 3D case in this paper sort of covered both cases on the same footing. And they sort of have a parameter sigma that would sort of appear in and out of these brackets to treat both. But this is all just for the anti-twisted case. And another crucial fact, again, this is sort of a technical point. You don't get such a nice answer. You sort of get stuck early on if there's not a particular quantization condition on this R charge, which basically comes from the requirement that you have a so-called well-defined line Orby bundle over the spindle. So that was method 1. I'll quickly go through method 2. It's probably a little more, a more modern method, and in some sense more elegant as well. It sort of gets you to the result faster, and that's to use equivariant index theory. So this was sort of all the way back in mathematical literature in the 80s to understand that equivariant integrals localize and can be written in terms of an index. So I've written here the index of an operator on a manifold M. So you compute the index with respect to action of a Lie group on the manifold, which also acts on bundles. And I've just written my Lie group element in the following way, including this supercharge operator and this equivariant parameter again. And I've written the result on the right-hand side here, where the sort of the fixed point set consists of discrete separated fixed points, which is the case for the spindle. The fixed points are the two poles. And essentially, you just compute this operator, and you have to write it in the following form, and then you can extract the one loop by just taking the product of these lambdas, which appear in this sort of exponential sum expression for the index. So there's a bit of structure here that I should probably explain. So gamma naught, I mean, this is a mathematically sort of sections of U1 valued line bundles, well, on the manifold. But really, we can think more physically as these are the bosons from the cohomological complex. 2 minutes, great. And similarly, we have this gamma 1, which again can be defined in terms of sections over the bundle, but is really the fermions in the cohomological complex. And of course, the action of the Lie group induces some action on the manifold itself, and this is sort of encoded in this Jacobian factor that appears in the denominator of the index. So that was for manifolds, but of course we need orbifolds on the spindle, and orbifold indices have also been worked out back in the 90s, but have only again much more recently been applied to the spindle case. And so you see it essentially looks very similar to the manifold index, but picks up some extra structure due to the orbifolding. So you have this sort of averaging over these two integers, which describe the spindle. And then there's also some additional structure that appears in the map, coming from the fact that you're now working with, the complex plane modulo integers at the poles. And so you have to sort of put some extra structure here and sum over all integers modulo NP, where NP is, well, 1 for north, 1 for south. So as a technical comment, it's really important to use the regular gauge field. So we can't use the gauge field that I gave earlier. One needs to shift to look at something that's really regular at the poles to get this right. And again, it's also crucial to have this even integer quantization condition on the R charge. But the sort of punchline is that you get exactly the same result as when you use the eigenvalue method. So everything sort of seems working out nicely from these checks. Right, so just a final slide on some conclusions and future work. So we studied the partition function of these 2,2 theories on the spindle, and we've done it using 2 methods, and they agree, which is nice. But a third check is that you can also obtain this from dimensional reduction of the n equals 2 result along the circle. And so this also agrees, so there's sort of a third check here. So we really think we're running along the right lines. So some future directions, I mean, everything I discussed was for the d equals 5 minimal gauge case, which is always anti-twist. But you can also look at twist, so you could think about the STU solutions, which have this twist property. There's other things one could want to do, perhaps take the large n limit of these index that we've computed. I think we'll hear about this in a bit for a different solution. And this asks the question, maybe we could say something about a gravitational dual of a spindle, so where a spindle may be the conformal boundary of some ADS solution. There's also different directions that one could maybe push this in a more mathematical way. So the partition function of the 2 spheres related to the computation of world sheet instantons, Gromov-Witten invariance. Is there some sort of similar story that one could look at for orbifold type partition functions? And finally, just kind of an idea I had recently is that this calculation on sigma is perhaps going to be useful for, again, looking at localization on other manifolds. So one that could be interesting is the product of hyperbolic space with this spindle, which is, of course, the near horizon region of these Plebanski-Demiansky black holes. So, yeah, just an idea. But I'll stop there, and thanks for listening.